In this video, we're going to go ahead and cover section 10.8, graphs of polar equations, part of unit 10, topics in analytic geometry. A couple tips for this unit. You want to make sure that your graphs are as accurate as possible. If you do have graph paper, I recommend it, especially when you're doing your rings for the polar coordinates, simply because it can get a little crowded. Okay, so I'll kind of show you what I mean in just a bit. So we're going to start with example one. This one goes right into examples, and these are mostly worked out for us just because they do take some time to do. So example one, we're going to sketch the graph of the following. R is equal to 6 times cosine of theta. So to do these, what you want to do is you're going to pick some values of theta between 0 and 2 pi, and I went ahead and just picked the ones that I thought were easiest for this first one. You'll notice I'm using the pi over 4. So we have 0, pi 4s, pi halves, all the way up to 2 pi. And then for reference, I did kind of draw our unit circle. Remember that you do have this guy here that has all the angles and, coordinates for pi over 4. So you could also use this. I'm going to use this for some other examples. But for this one, I went ahead and just wrote it. So this is pi fourths, this is 2 pi fourths, 3 pi fourths, 4 pi fourths, which is pi, 5 pi fourths, 6 pi fourths, 7 pi fourths, and 8 pi fourths. And what we're doing is we're plugging in our value of theta. So for example, when theta is equal to 0, right here, we plug that into our angle and we get 6 times cosine of theta, which of course is just the x value. So 6 times 1 in this case is just equal to 6. So that first ordered pair is going to be 6 comma 0, where again 6 is my r and 0 is the theta. You do the same thing for all of them. I did show the work for all of these just to kind of show you what we're actually doing. Remember that when it comes to our points, we're looking at cosine, so we do have to look at the x values, in this case, all of the x's, okay? Just to kind of, go over a few more, let's say, I don't know, this one, 3 pi fourths, so we have 6 times cosine of 3 pi fourths. You look at 3 pi fourths, which is 1, 2, 3, this one, and we have negative square root of 2 over 2, so that's what I plugged in to replace basically all of this part. So 6 times negative square root of 2 over 2, 6 over 2 is negative 3. So we have negative 3 square root of 2 with our angle of 3 pi fourths. And again, that's the next ordered pair. So we did that for all of these. And what we're going to do is we're going to actually plot them below. So down here, I do have a graph ready for us. And this one, I did not put the rings. And I kind of did that on purpose so you can see the difference between having the rings and not having the rings. And, if you're very neat, then this might be no problem. I tried to make this somewhat neat, so we'll see how it comes out, okay? The lines that I drew here are going to be our pi fourth. So this is like pi over 4. This is 3 pi over 4, and so forth. Remember that when we do have the negative r values, that is going, depending where we start, let's say we had negative 5 or something, 1, 2, 3, about here, then pi over 4 would be this one, okay? So just remember, keep that in mind. So we're going to start with the first one. Our first point was 6 comma 0. So we have 6 and then an angle of 0. So there's our first point right here. And then we have 3 square root of 2 pi fourths. So 3 square root of 2 is about, I have no idea actually. I want to say it's 4 point something. I want to say 4.7 or so. So we're going to go ahead and, you know what, let's calculate it. We don't want to get this wrong. Let me go ahead and calculate real quick. So 3 and then square root of 2 multiply. Yeah, 4.2. So I wasn't too far off. So this is about 4.2. So 4 and then 0.2 is about about right here-ish. And that one is at pi fourth. So if I think of it like a circle, it's going to land maybe somewhere right here. Okay, and again, if your circles are not perfect, not that they have to be perfect, but somewhat okay, then this might be a little bit off. So mine might be a little bit off, but the general shape should still take form. Next one we have 0 pi over 2, and again, I'm just getting from here to 0 pi half. So when r is equal to 0, we are at pi halves, and that's going to just be here right in the center. And then we have negative 3 square root of 2, which is going to be that negative, what did I say it was? Negative 4.2. So negative 4.2, 1, 2, 3, 4. negative 4.2-ish right here. And my angle for that was 3 pi fourths. So 1 pi fourths, here, let me move out a little bit here. So 1, 2, 3, 4, 4.2, 1 pi fourths, 3 pi fourths. I'm sorry, 2 pi fourths, 3 pi fourths. So somewhere over here-ish. Okay. And then we have negative 6 pi. So negative 6 is on this side. 1, 2, 3, 4, 5, 6. But since we started over here, pi is actually going to be all the way over here. So you see how I mentioned earlier, depending where you're starting, you have to remember how to plot polars from last week's notes. And pi is going to land over here. So it actually lands on the same spot that we already have here. We have next negative 3 square root of 2, which is again negative 4.25 pi fourths. So that would be, let me see, so 1, 2, 3, 4, about here. Negative 5 pi fourths would be 1, 2, 3, 4, 5. So we already have it right here. So it's actually the same point we have there. Then we have 0, 3 pi over 2, which again is going to be right in the middle. 3 square root of 2, 7 pi fourths, which is my 4.27 point, sorry, 4.2, and then 7 pi fourths. So 4.2, 7 pi fourths is all the way around and it lands in the same spot. So it looks like we're just kind of repeating the same points here. You can check the last one, 6 to 2 pi, so 6 and then 2 pi. So it looks like our shape is actually kind of like this. You can connect all of these at this point. And this is the thing about polar, when we're graphing polar equations, they tend to make these like really curved pictures. This should be kind of like a circle, but you know, my points are probably a little bit off. But yeah, there's that one. It's kind of like a circle or oval looking thing. You're going to see we're going to have some pretty interesting ones in the next examples. The last example I did not get to do because it was a little complicated, but we'll definitely do that one in class. And that one is a rose petal pattern, which is kind of cool. So let's go ahead and look at the next example. And again, like I mentioned, a lot of these are worked out for us. Oh, actually, before we have an example, we do have some more notes here about symmetry. This is symmetry, zeros, and maximum values. This kind of goes back to a little bit of what we did in the first semester with symmetry. We used to have, or we talked about symmetry with the x-axis, the y-axis, and the origin. We know that the symmetry over the y-axis is known as even symmetry, where you kind of have like a reflection going over this way. When you have symmetry over the origin, it's almost diagonal. Then we just have symmetry over the x-axis. Here in polars, we have similar ideas, but it's symmetry with respect to the angles. So in this first case, we have symmetry with respect to the line theta is equal to pi over 2. So it's kind of like our even symmetry, kind of. We don't want to call it the same thing, but it's with respect to this line. So everything on this side is going to match everything on the left side, and vice versa. Okay. Then we have symmetry with respect to the polar axis, which is kind of like, respect to the x-axis. Everything on the top is going to match everything on the bottom. So you have this going on. By the way, the notation we have here is just the notation for the coordinates. So for example, if we have a point up here, our theta, if you flip it over, it becomes r negative theta because, well, in quadrant 4, our angles are negative, yeah? So, well, in this case, if we go, clockwise, okay? Last one you're going to have is symmetry with respect to the pole. Remember that the pole is just kind of like our origin. So again, there's that kind of similar symmetry pattern that we have where you have odd symmetry, which is with respect to the origin. Here it's called respect to the pole. So everything on this quadrant is going to flip over to this quadrant where both of these are going to just kind of, and actually this should be negative, I'm sorry. That should be negative. We're going to switch signs, okay? And yeah, that's kind of a visual of what we're going to be looking at in just a bit. And why is this useful? Well, this is useful because you can go ahead and kind of start copying this while I'm explaining. It's useful because when we're trying to graph polar equations, we don't want to do, a list of a million, I don't want to say a million, but a whole bunch of angles. It takes some time, yeah? I'm going to do that maybe just one more time, and then after that, I am going to use symmetry to kind of make our life a little easier and not have to work so much to get that picture out, that graph. Okay, so let's take a look at some of the tests for these symmetry patterns that we see. We have that it's the equation is symmetric with respect to the following, and we can use the following substitution. So if it's over the line, theta equals pi over 2, we can replace our theta with this or this. So whichever one you prefer. Same thing with the polar axis, we can replace it with something a little bit different where r is positive and theta is negative. So this is kind of like your even symmetry. I don't know if you noticed, but our r's are the same, but our thetas are different. So if this is like x and y, x would be the same, and then your y would be the opposite sign because you're just flipping over the y-axis. Yeah. Um, Something similar to that. And I'm sorry, not the y-axis, the x-axis. What am I saying? The x-axis. So you have your opposite y values. You'll have to forgive me. It's a little bit late right now, so having a bit of a moment. Last one that you have is the pole, and this one is the one that I mentioned earlier. Where again, this one, pretty sure that one should be negative. I'll have to double check, but I'm pretty sure it needs to be negative here. Oh, you know what? No, I'm sorry. It's not negative. I'm thinking x and y. So this is positive because when you start on the negative side, remember that the negative will make the angle still go counterclockwise, which means that the one up here that I changed earlier should be not that one. This one. This one should be positive. My bad. My bad. Okay. Next one. So these are just definitions showing you what the symmetry is going to look like. And now we're going to actually see it in action with example number 2. And again, this one's kind of worked out for us except for the graph. So what I tried to do is leave the graph for us to do together simply because that's the part that tends to kind of overwhelm students, myself included when I was your age. So let's look at example 2. We have use symmetry to sketch the graph of r equals 3 plus 2 sine theta. So just by looking at this, I know from my past experiences that the sine function is an odd function. So I would probably go with something of that definition, and we can definitely derive that in class on how to get this algebraically. But to prove that it's odd and it's going to fall into the formula that goes with that, which would be if we look over here again, okay, you remember me kind of switching the signs over here. When we have odd symmetry just in general, what happens is your x and your y in one quadrant will flip signs. So if this was an x and a y, if I was going to flip it over for odd symmetry, it would be negative x, negative y. So that's why for polars, what happens is the signs flip for r and theta. So you'll notice you have, the positives here, you have negatives here. So that's kind of what I'm going with here, where I know that this right here is going to match up somehow, which means we're going to probably have symmetry with respect to this line. It's kind of a little confusing, but like I said, you have to go back to your definitions of odd and even. And even if you did not know that, okay, here's what we do. We make a list. Yeah, we make a list of all the angles between 0 and 2 pi. Not all the angles, but the main ones. And what I did for this one is I went ahead and used my pi over 6 and pi over 3 this time. And I did fill it in. I can kind of go over a couple of those if you'd like, just so you can see what I came up with. We did pi over 6, pi over 3, pi halves, which is basically, and let me actually show you here. I'm going to show you with this one. Okay, so let me fold that one back. Because this one has, even though we don't see pi over 3, we know that pi over 3 is a multiple of pi over 6. It's just 2 pi over 6. So pi over 6, pi over 3, 2 pi over 3, 5 pi over 6, and so forth. And if you're just thinking in terms of pi over 6, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is the same as 2 pi over 6. I'm sorry, which is the same as 2 pi. 12 pi over 6 is the same as 2 pi. So we can use this, and I went ahead and did that for these values. So for instance, we have pi over 6. If I plug in pi over 6 into my theta, well, that's just going to be the first one, right? So here my y value is 1/2, and I'm using y because, again, we're using the sine function. So remember that sine is y, cosine is x. I believe the ones in your textbook, the ones that are shown are cosine. So we're doing the ones that are not shown, which is sine. Okay, but we might do one of cosine just so you can see what it looks like in class. But anyway, yeah, so you just plug it in. So we get 3 plus 2 times a half. 2 times a half is just 1. So 3 plus 1 is 4. The same thing right here. We find pi over 3, which is going to be this second one here because 2 pi over 6 is the same as pi over 3. And if you don't like that, you can also look at the pi over 3 one, which is right below, right there. Yeah. And my sine value for there is square root of 3 over 2. So I plug that one in. My 2's are just equal to 1. So I have 3 plus square root of 3, which is approximately 4.7. Okay. And you kind of do the same thing, you just plug everything in. So you see that I did that for all these values. And before I even go to the graph, you will notice that there is, in fact, some kind of symmetry going on here. You have same values for a few of them. Yeah, you have the same values for these two, for these two, and you jump down this way, and you have same values here, here, and here. And you're going to notice right now when we graph this that it's actually going to be symmetrical about that line pi over 2, which is kind of like our even symmetry that we used to see before. Now, I know I said that sine has odd symmetry, and it does, but the thing is we use that to try to figure out which of these over here I would be plugging into, okay? And word to the wise, this trick as far as try to figure out which kind of symmetry it is by plugging into the patterns we have on this side, it doesn't always work, which is why I didn't do it for this one. I kind of wanted just to go with, proving it to you and then showing you something else on the next page, which is going to make your life a little easier. Okay, anyway, let's go ahead and get to graphing this. You'll notice on this graph, I did do the circles. They're not, too pretty, but they're all right. You'll notice I also did some lines. So this line right here, I'm saying is pi over 6. This is pi over 3. This would be 2 pi over 3. This would be 5 pi over 6, and so forth. Remember that, let me see, 7 pi over 6. Remember that if we have a negative r value, that these angles change, right? It depends where we start. So just keep that in mind. I don't think we have any negatives, so it shouldn't affect us, but just in case. So let's go ahead and see. We have, I'm just going to jump right into it. For the first one, we have 4 and then pi over 6. So we're thinking r theta. And I didn't write this part kind of on purpose, but we can do a couple. So we have 4 comma pi over 6. So 1, 2, 3, 4, and then pi over 6 is right here. So there's my first point. For my next one, I have 4.7 and then pi over 3. So 4.7-ish, and then pi thirds. It's actually 3 plus square root of 3, but that's kind of hard to see here. So 4.7, 1, 2, 3, 4 point, about right there. And then it's at pi over 3. So it's going to be all the way about maybe right here. Okay. And then we have 5. I'm just going to do one more. 5 and then pi halves. I'm just getting this number and this number is what I'm doing. So 5, 1, 2, 3, 4, 5, and then all the way to pi over 2 right there. Okay. And you should kind of connect it as you go. I'm going to wait till the end till I connect it, but that's what we're doing essentially. Then we have 4.72 pi thirds. So see, 4.7, again, it was like this one, and 2 pi thirds is about right here. So far we kind of have like a somewhat circle going on-ish. Not quite a circle, but something like that. 4, 5 pi over 6. So I know 5 pi over 6 is over here. So let's see. 1, 2, 3, 4, 5 pi over 6. There we go. Then we have 3 pi. So 1, 2, 3, go around to pi. 2, 7 pi over 6. So 1, 2, go around to 7 pi over 6. And you're noticing that it's kind of starting to like close in this way. Interesting, right? 1.27, which is the same as 3 minus square root of 3, is at 4 pi thirds. So 1.27, here's 1. 1.27, maybe about right there somewhere, come around all the way to 4 pi thirds, which is about right here. I didn't label that one, but it's 4 pi thirds. And then we have, let me move this down just a little bit. Then we have, where was I? 1, 3 pi halves. So 1 is right here, and we're going to go all the way around to 3 pi over 2, which is right there. So take a look, kind of interesting, yeah? 1.27 again, 5 pi over 3. So 1.27, 5 pi over 3, I want to say is going to be right here. because remember this one is 2 pi, which is the same as 6 pi over 3. So that's my 5. So it was, what was it? 1.27 and then 5 pi over 3. So about right there. And here you'll start to notice, well, this one should be more, they should be kind of similar, but you'll start to notice that there is this symmetry going on here. Okay, look, we have all the points are kind of matching. I'm thinking of music here. 2, 11 pi over 6, so 1, 2, 11 pi over 6, and again, there's that symmetry, assuming my lines were perfect. And last but not least, we have 3, 2 pi's, so 2, 3, and 2 pi's right here. So we have something kind of like, and I'm going to use a different color on this one, if I can find my pen. Where did I put it? Oh, I'll just use blue, it's fine. So I'm going to go ahead and use a different color to kind of show you what the graph looks like. And you will be amazed because these are some pretty weird looking graphs, but they're kind of cool once you get past all the pickiness, right? There you go. So it's kind of like a, I don't know, upside down apple looking type of deal. And it's actually called a Lima Cone or Lima, I'm not sure how to pronounce it, but I'll show it to you right now, the pronunciation. But you can see here that we do have that symmetry over the line pi over 2. So what I would definitely make a note here and say that there is symmetry with respect to the line. I'm just going to put to line theta is equal to pi halves. Because if you were to fold this like that, it would, land on itself. But yeah, there is the graph. And let me go ahead and show you the bottom. I did put a note down here about what I'm talking about with what it's called. It's called a Lima cone or Lima cone. I'm not really sure how to pronounce it, but there you go. Okay. There are several different types of polar graphs you're going to see. We're not going to cover all of them in this video. Like I said, we're going to cover another one that looks kind of like this. It's going to have like a loop. And we're going to cover one more in class that looks like it's called a rose petal. That one's kind of neat too. Couple more things. And I did mention this earlier. I said there's another way to check the symmetry, and that was kind of what I mentioned with sine and cosine. We have some quick tests for symmetry. Basically, if you have a sine thing going on, so r is equal to some function in terms of sine, it's symmetric to the line theta equals pi over 2. So kind of what you saw here, where you have a reflection going over the vertical axis. Okay. If it's a cosine type of function, then it's with respect to the polar axis, which means we're going to have this other over the x, well, not x, but over the horizontal axis, so to speak. Okay. Let's jump right into an example. This one is the last example in the video. Like I said, these do take some time to do. You'll notice even though a lot of them are worked out, it's still taking some time. Yeah. So this one, I left a few spots open so we can kind of do those together. Example number 3 is to sketch the graph of r equals 1 plus 2 sine theta. So with this one, what we're going to do is we're going to find zeros, maximums, and then also use what we know about the symmetry. So I don't even know if I mentioned that, but the title of this little subtitle was the quick test for symmetry in polar coordinates. And this does have to deal with zeros and maximums as well. You don't necessarily need them. You could still find all the points just by doing what we did before. But I did want to give you that information, just in case it makes your life a little easier. So first of all, this one is a sine function. So that tells me right away that I know it's going to be with respect to the line theta is equal to pi over 2 because sine is odd and for the odd coordinates, those coordinates match up with my test for pi over 2. So in other words, you're going to have that reflection over the y-axis. No, sorry, I keep saying y, over the vertical axis. For the zero, okay, what we're going to do is we're going to do what we always do when we look for zeros. You set the equation equal to 0. So in this case, what I did is I went ahead and said r equal to 0. So we have 0 is equal to this, and we're just going to solve it real quickly. So minus 1 to both sides, we get negative 1 is equal to 2 sine of theta, divide by 2 both sides, which gives us sine of theta is equal to negative 1/2. And then, of course, at this point, you want to ask yourself, at what angle is theta equal to negative 1/2? So I know, and actually, let me get my foldable here so we can see. let's see, where is y equal to negative 1 over 2? So not here, not here, here, right here and here. So I'm going to focus on this side because it's just the one that I happen to look at first. So this value right here is going to be 11 pi over 6. I can tell that because I know that it's one slice away from 2 pi. And since we're thinking in terms of pi over 6 for this one, 2 pi is the same as 12 pi over 2. So minus 1 is 11 pi over 6. Yeah? So theta is equal to 11 pi over 6 or 7 pi over 6 because, well, we know what happens over here on this side too. Yeah? 1, 2, 3, 4, 5, 6, 7. 8, 9, 10, 11. Okay, so that's where I get my points from. Which means that when r equals 0, theta is equal to one of those two. I'm going to stick with 11 pi over 6. Okay, and the reason I'm doing that is because I'm kind of thinking on the values that I'm going to choose. I'm going to choose everything on the right side of the graph because everything on the right side has to match everything on the left side because this has symmetry over pi over 2. So I'm going to stick with 11 pi over 6 because it's on the right side. Okay. For the maximum value, this part's a little bit more, I don't want to say involved, but you have to kind of dig a little bit back into what you remember about the sine function in this case, and you're trying to think of where at what angle is this function, the one that I have here, where does it have a maximum? So the easiest way I thought to do this was to go ahead and think of it as your original Cartesian graph. So by original view here, I mean, think of it in terms of y. So if this was y equals 1 plus 2 sine of x, well, we know, or maybe we remember, that my sine function is generally located between -1 and 1. So I kind of have that very lightly sketched here. And I do have it over a period of well, 2.5, but here's 0, and then there's pi, and then it's kind of hard to see. But let me make it a little bit darker. Yeah, this is pi, this is 2 pi, and that's my OG sine function, my original graph, yeah? And what I did, let me get this to focus, is I went ahead and did the 2. So the 2 in the front is an amplitude of 2, which means that it's going to get multiplied by 2. So you'll notice that the other part, the part that's like a little bit darker, this is times 2. So this went up 1 times 1, I'm sorry, 1 times 2 is 2. So there's that one, and this one became -2. So it just kind of gets vertically stretched by 2, yeah? Then we have the 1 plus. I didn't do that part because I wanted to show that part to you. The 1 in the front means we're going to shift the entire graph up by 1 unit. So at this point, this one goes up by 1, this one goes up by 1, this goes up by 1, and we kind of have something like that. Let me see, up by 1. Oh, wait, a little bit off here. Yeah, you get the idea. So it's something like that, yeah? And you will notice that once we've done that transformation where you put the 1, well, now the new maximum point is going to be 3. So that means that we have a max at, well, if we're thinking in terms of the other thing, well, we know that it's going to be at theta equals, my angle here is pi over 2. So we don't have x and y. Remember, for this one, we just use x and y for the sake of trying to find that maximum. But for this one, if theta equals pi halves, then our r is going to be equal to 3. Okay, so this is another pair that we have. So far, we have this coordinate and we have this coordinate. Now, again, do you have to do this? No, you don't. You can actually just probably, pick the points, and you'll find these points at some point. But if the problem does specifically ask, what is the maximum for this value, then this is how you would do it. Okay, go ahead and look at the last part of this problem. I went ahead and, as you can see, I already have the points chosen because of the time. So you'll notice that here's my 11 pi over 6 and 0, and that's my 0 that I found. And I did not include 7 pi over 6 because, again, I'm using the right side of the graph. And I also have my r. Let me see yeah, here we go. So when r is equal to 3, we have our angle of pi over 2, which is what we found on the other one. And this one is also, it was the max that I found. Okay, so I went ahead and chose values between 0 and 2 pi. that are basically on the right side of the graph. And again, the reason I did that is because of that symmetry that I know is going to happen from this side to the other side. So these are the values I chose, and this is what I got after I plugged it in. This is this right here, and I didn't mean to do this, but I kind of did, and I was like, I'm just going to show it to them. This is all my side work. Yeah, so when I try to do this without doing too much work, I'll kind of put this on the side. So this is like 1 plus 2 sine of 0, that gave me 1. 1 plus 2 sine of pi over 6, it gave me 2. And again, I did use this because I don't have the entire unit circle memorized. I kind of just have the first quadrant. But I know that, we have the reflective properties. So you can use this or any other unit circle that you might have if you lost this. So yeah, we have all our values. We found them the same way we did the one before. And now we're just going to plot this. So let's go ahead and finish this graph up. We have our circle, and this one I tried to make it even better, but as you can tell, I kind of messed up here. Let's go ahead and graph this one. This one does look a little bit weird. So what I did is I started with 0, 1 because that's my first value. So 0, 1. So let's go ahead and do that. Well, 0, 1 where theta is equal to 0. So at my first ring, okay, I have a angle of 0. So there's the first point. My second value here, and I'm going to be kind of going back and forth, is pi over 6 and 2. So when r is equal to 2, theta is pi over 6. So here's 2, and I don't have my cross section, so let me actually do that real quick. Let's say this is pi over 6, and what I'm going to do is I'm just going to extend it. Hopefully it's not too unstraight. And we'll say this is pi over 6. We'll say that this one is, oh my gosh, it's a little crooked, pi over 3, and I'm just going to extend it down this way also. And same thing on this side. So this would be, let's see, pi over 6, 2 pi over 6, 3 pi over 6, 4, 5. And then the other one would be 2 pi over 3. And of course, the more accurate you draw your lines, the better picture you'll get. But we're just kind of sketching right now. All right, and then, yeah, there we go. So, oh, let's see what else I have. I have 5. Okay, I guess I can do the other ones. So since I have some of these other ones, I'm going to go ahead and plot those as well. I have, let's see, 11 pi over 6 would be over here, and then 5 pi over 3 would be about right here. Let's see what I'm doing. 5 pi over 3. Okay, so I wanted to make sure that I did have for sure this side, because like again I said, the symmetry is with respect to pi over 2, which means all these points are going to reflect over this way. So let's go ahead and see the next one. So I said 2 pi over 6, right? So that's the second ring, and then pi over 6 is about right here. So if I have something kind of like, I'll outline it right now, okay? I don't want to mess it up so early. So then we have 0.7 pi over 3. 0.7 is approximately 1 plus square root of 3. So just so you know, I do use the decimals for this part just for the sake of graphing, okay? But 0.7 pi over 3, so now I have 0.7 is going to be about a little bit below 1, and it's going to be about right here. Well, let me see. Yeah, 0.7. Then I have 3 pi over 2, so here's my third ring, pi over 2. Okay. And then I also have, let's see what else. I have -1, -1, 3 pi halves. So that's going to be, that was a little interesting because we have -1, but remember that since we're going, it's a negative number, 3 pi halves is going to go all the way around. So you're thinking -1, then pi halves, 3 pi halves. So it's actually up here. Yeah. Okay. What else? What else? You know what? Let me double check one thing. I'm pretty sure this one shouldn't be 0.7, but let me just check. So 3 square root 1 plus. Yeah, that's what I thought. Okay, I have to fix one, but I'll fix it right now. Let's move on. And then we have 5 pi over 3, -0.7. So we're going to go to -0.7 and then find this angle. So -0.7 is about right here, and then 5 pi over 3. Remember that we're going the opposite direction. So 5 pi over 3 would be all the way around. So 1, 2, 3. Oh, wait, I'm losing my spot here. 1, 1, 2, 3, 4. Okay, so it's going to land about here-ish. 0.7, about right here somewhere. Okay, and then let me see what else. We already did that one. Did we do? Actually, no, we didn't do. I'm sorry. So as you can see, these can get a little tedious. That's why I'm making sure I get all the points right. 11 pi over 6 and 0. So we're thinking at 0, it's 11 pi over 6. So a radius of 0 is going to be basically in the middle. And then 2 pi 1. So for this one right here, we have a radius of 1, and it's at 2 pi, so it's in the same spot that we had here. Now there was one that I needed to fix, and that was going to be the 0.7, because I'm pretty sure it's supposed to be bigger. So this one right here, pi over 3.7, it's 1 plus this value, so it actually comes out to 2.7. So I forgot to add for some reason, but it's 2.7. So that one was this one. So let's just pretend that didn't happen there. And that one should be 2.7 pi over 3. So that would be 2.7 pi over 3. That looks better. Okay, yeah, so pretend that one's not there. My bad. So what we have is we have something kind of like this. These three were kind of our first ones. And I'm going to reflect them over. So like this one should be kind of like right here somewhere. This one's going to be here, and so forth. And then these ones right here, we have one right there. So we kind of have this like little thing going on here. And then this one, I'm pretty sure should be higher up as well. What point was this? Let's double check that one. I think it was 5 pi over negative 0.75 pi over 3. Okay, so let's just check one more time. Negative 0.7. Okay, so this right here, and then 5 pi over 3. So 1, 2, 3, 4, 5. You know what? Yeah, it should be up here, not there. Oof, talk about two mistakes. Okay, well, anyway, so we have something kind of like this. By the way, if I did lose you, just let me know. Like I said, this is kind of it's a kind of an interesting topic, yeah? You'll notice we have the outer like ring, so to speak, and then we have these three on the inside. So remember, this one's bad. These two are, well, actually, this one actually does line perfectly because we have symmetry there. But we have these rings here in the middle, and what happens is this what is called the inner loop. So you actually have something kind of like this. Let me outline in a different color so you can see it. It will look kind of like an egg, maybe. I don't know how else to describe it. With like a little, I don't know, loop in the inside the stem, maybe. And it looks like that. So they're really pretty. One of the things about these equations that once you do get them right, they come out really nice. And this is a really great show of how math is kind of beautiful. Yeah. So yeah, that's it. And this is also an example, by the way, of a Lima cone or Lima cone, however you say it. So there you go. Hopefully I didn't lose you with those points. If I did, just let me know. Remember again that when we have our negative angles that you do have to go backwards, so to speak. So there you go. We do have one more example. I'm going to go ahead and let you just copy. Well, let me get the whole thing here so you can see the whole thing. There's the graph. And here is the work. There's one more example I want you to write down just for the sake of having it. And we're going to go ahead and do this one in class, albeit very slowly because as you can see, it's very easy to make mistakes on these. And this one is going to be an example of a rose petal. I might change it to a cosine function. We'll see, just because, like I said, the cosine functions are actually done in the book. So if you want to take a look at those, by all means. I went ahead and did the ones that are not worked out. That way you have, two different ways of seeing it. That's all I have, guys. I do apologize if it's a little bit off. It's a little late, so you got to forgive me. But that's it for this. If you have any questions, as always, please just let me know.